Okay, we're going to consider some new integrals. But first, let's consider some old integrals. We're well aware of how to do something like integral e to the x dx is just its own integral, plus a constant. And then something like integral of x e to the x squared, that could be done with a u substitution, where u is x squared, then du would be 2x. This is the kind of thing that I've been talking about we need to be able to do in our head. You probably don't need to do a u substitution there. You can just think in your head how that would work. That's 1/2 e to the x squared plus c. Now let's think about something like x e to the 6x. This is very similar to x e to the x squared, but now if you let u be 6x and you took the derivative, du would just be 6, and we didn't get that x that's out in front. So what are we to do? Well, that's what today is about. So this doesn't seem to have a lot to do with it, but consider the function x over 6 e to the 6x. Where did I get that? Well, if you take that function's derivative, you get x e to the 6x as one of the parts from the product rule. And then the other part of the product rule is going to give you 1 over 6 e to the 6x. Well, that part that we want, let's isolate that on its own and subtract the 1/6 e to the 6x over to the other side. So now x e to the 6x is the derivative with respect to x of x over 6 e to the 6x minus 1/6 e to the 6x. If we integrate everything, integrate both sides, and then the integral is a linear operator, so we can split things up over here. So everything's fine. Just integrate every single term. We get the integral that we want is the integral of the derivative of x over 6 e to the 6x. Well, that is the function back, right? X over 6 e to the 6x. And then we integrate 1/6 e to the 6x. Well, that's going to again divide by 6 when we do that, and we get a 1/36 e to the 6x plus a constant. So in a roundabout way, we were able to find the integral of x e to the 6x by kind of doing the product rule and kind of ripping it apart. It's a little weird what we did. Well, basically, this thing is something we're going to call integration by parts. Let's look at it in a little more generality. So kind of generically, what we did was we started with the product rule. And what we're trying to find eventually is the integral of fg prime or f prime g. It really doesn't matter how you label these things. We have two of the functions here, but we'll say we're trying to find the integral of fg prime in the end. So if you have fg prime, you get f prime of g plus fg prime. That's from the product rule. And then you integrate everything. Well, the integral of fg prime dx just gives you fg back. And now we're going to solve for the one that we want, which is integral of fg prime dx. You get that to be fg minus integral f prime times g dx. That's just a little messy, but this is our integration by parts formula that we're going to end up with. The way you usually see that written is we're going to rewrite f of x as u and g of x as v. Then du is f prime of x dx, and dv is g prime of x dx. So this formula up here becomes exactly integral of u dv is uv minus integral of v du. This is our integration by parts formula. This is one of the things that you definitely need to know through the rest of this class and into the next class. This is a pretty important formula. This opens up a world of what are rather simple looking integrals that we simply could not do before. Let's take a look at another example. One thing to keep in mind when you're doing this is that whatever you pick for u is going to get differentiated. which often means it's going to get simpler. If it's something like 3t plus 5, that becomes a 3, right? Whereas whatever you pick to be dv, because those are your initial choices, one of these is u and one of these is dv, is going to get integrated. So you want something that doesn't get too crazy when you integrate it, right? So you're looking for u to get simpler when you differentiate it, and dv to not be ridiculously terrible when you integrate it. So that's kind of what's going on here. So we made a choice that u was going to be 3t plus 5, then du is 3dt, dv is our cosine t over 4 dt, and then our v is for sine of t over 4. So this is always going to be set up as the integral of u dv. Right? That's the beginning of our formula. So you have to choose from what we have there, one of those to be u, one to be dv. That's basically what's going to happen to start integration by parts. Then you just use the formula. Well, uv, pretty straightforward, 3t plus 5 times 4 sine t over 4. And then there's an integral to do with the v du. So here, that's going to be the integral of 4 sine t over 4 times 3 dt. Well, when you integrate that, you're going to get another 4 brought out here. It's going to give you 16 times 3 is 48 cosine t over 4 plus a constant. This sign had to change in that process too. There's our final integration. We had no way to do this problem before today. It's pretty cool. Let's take a look at another example. Integral of w squared sine of 10w dw. A lot of the examples you're going to see are trig functions and exponential functions. The reason for that is we know how those integrals work, but when the wrong thing gets chained out here, we can't do it because the u substitution is not going to work. So on this one, a u substitution wouldn't work because there's no way you would get a w squared out there if you made u like 10w, right? You would just get a 10. So we've got problems. Well, we're going to make u w squared because that's going to get simpler when you differentiate it. And we're going to make dv sine of 10w. That's not horrible when you integrate it, right? Those are kind of how these choices work. Sometimes both ways will work on integration by parts. But anyway, that's what we're going to do. Skipping a little bit of details here, this is our integral that we're working out. The uv w squared times minus 1/10 cosine 10w. But now look at the integral of v du. You end up integrating 1/10. I changed, this was a minus sign in the formula, but this is a minus sign, so we change it to plus. Integrating 1/10 cosine 10w times 2w dw. Well, if you multiply, that's a 1/5 w cosine 10w. Right here, you can see that right there. Well, that integral is also going to require integration by parts. We're going to have u be w, du is dw, dv is cosine 10w dw, and v then is 1/10 sine of 10w. Now you've got to put it all together. We have our first part that was fine. We have 1/5 of the integration by parts that we had to do here, which is uv, w over 10 sine of 10w, minus 1/10 integral sine of 10w dw when you do v du. Well, if you work that stuff out, you end up with negative w squared over 10 cosine 10w plus w over 50 sine of 10w plus 1/500th cosine 10w plus c. Okay. So that one, you actually had to do repeated integration by parts. That is not that odd. That happens quite often. Two more examples. Integral of natural log of x dx. This is a little weird because we don't have two functions here. Well, what if we said u was 1 and dv was natural log of x dx? then we could say du would be 0, and v would be the integral of natural log of x dx. Oh wait, that's a bad choice because we can't do this problem unless we can do this problem. So we've just kind of put ourselves in a little bit of a circle here. So let's try something else. What if u was natural log x and dv was dx? Then du is 1 over x dx and v is x. Oh, this totally works. Then from the integration by parts formula, the integral of natural log of dx is uv x natural log x minus the integral of v du. So that's the integral of x times 1 over x dx. Well, x times 1 over x is just 1. So this integral is just x. So this is x natural log x minus x plus a constant. The last one we're going to do is one that you could do with a u substitution. But we're not going to do it with the u substitution. We're actually going to work this out. Oh, by the way, the u substitution, I think here would be u is x plus 1. Then this would become u, and this would be u minus 1 times square root of u, which is u minus 1 times u to the 1/2, and you could break everything down in terms of rational exponents and work it out. But we can do it with integration by parts. Again, this will make a nice derivative here, so u and du. And this is not a terrible integral. Square root x plus 1 becomes 2/3 x plus 1 to the 3/2. So we're going to integrate. X square root x plus 1 by integration by parts is 2/3 x plus 1 to the 3/2 minus the integral of 2/3 x plus 1 to the 3/2 dx. So uv minus v du. All right. Well, this integral requires a little bit of work. That's going to go up to the 5/2 but get multiplied by a 2/5. So you're going to get a 4/15 x plus 1 to the 5/2 plus a constant to go along with this part we already had. Alright, so I think you will find this is something that you will use quite a bit going forward. It won't work on every problem. That's why there's a whole chapter 7 of different integration techniques. But this is one that works quite often. And you really just need to remember that it comes from the product rule. I have to rederive it every once in a while. But for our purposes, you really should memorize integral u dv is uv minus integral v du. I would work on memorizing that. But if you ever do forget it, you could start with the product rule, start with uv, take its derivative, and work from there if you need to. But it's probably better just to memorize the formula for now. Okay, that is it for the video. There are some try problems and stuff, but we're going to stop right there.